We're looking at the population of endangered bird species that's decreasing at a rate of 0.75% per year. There are currently 200,000 of these birds. Write a function that models the bird population. How many birds will there be in 100 years? So when I'm reading the word problem, I'm looking for keywords, and I see decreasing, so I know it's decay. So instead of 1 plus r, I'm going to use my growth or decay factor as 1 minus r. Or my b value. And it's important to remember it's 1 minus r. The rate is 0.75%. So again, I have to convert that rate into a decimal. So divide by 100 or move the decimal places 2 points to the left, and I get 0.0075. So when I'm coming up with my decay factor, I am subtracting that from 1. I'm not just putting that in as my b value. And I can leave it like that, or I can do the math out to create a single number, which would be 0.9925. So I know my starting amount was 200,000 birds. I know my decay factor now is 0.9925. So for any model, I'm going to use x as my exponent. So this is the equation that models my situation. The second part, how many birds will there be in 100 years? If this is decreasing at a rate of per year, then years is my time, which is going to become my exponent. So instead of x, I'm going to have an exponent of 100. And again, you'll need your calculator. So you're going to raise the parentheses to the exponent of 100. So 0.9925 to the 100th power. It's about 0.47. And you're going to multiply that by 200,000. And you would get 94,206. And again, we are talking about birds. So we're not going to have fractional. So we'll leave it as 94,206 birds in 100 years. So if you know it's decreasing and it's decay, your final number should be less than your starting amount. If it's growth and increasing, then your final number will be greater than your starting amount. It's a quick way to check to make sure you've got your growth or decay factor correct, whether it's greater than 1 or less than 1. So now we're going to take a look at working with exponential growth and decay with a table. So in a science fiction novel, the main character found a mysterious rock that decreased in size each day. The table shows the part of the rock that remained at noon on successive days. And we want to find out what fraction of the rock will remain at noon on day 7. So I'm looking at this, and there are multiple ways I can attack this problem. Looking at my fractional portion of the rock remaining, I can see it's going down in size. So I know I'm going to have a decay factor that has to be less than 1. I know my starting amount is 1, which represents the whole part of the rock. But I have to find that decay factor so I can create an equation so I can find on day 7. Or I need to extend my table and continue with that decay factor, also known as your constant multiplier. So what am I multiplying by each time? So to get from 1 to 1/2, what am I multiplying by? From 1/2 to 1/4, what am I multiplying by? 1/4 to 1/8, what am I multiplying by? Remember, this is a constant multiplier, meaning it will be multiplied by the same number every single time. And the way we find this is by doing the opposite of multiplication, which is division. So I'm going to take my lowest number, or the number at the bottom of the table, 1/8. I'm going to divide that by 1/4. A 1/8 divided by 1/4 is equivalent to 1/2. So to get from 1/4 to 1/8, I multiply by a half. I'm going to double check to make sure this is constant. I'm going to do 1/4 divided by a half. And that is also a half. And finally, 1/2 divided by 1, which is a half. So I do have a constant multiplier. That constant multiplier is also my b-value. So now I have enough to figure out what this equation is going to be. My starting amount is 1. I'm multiplying by a half every day. And in this case, I want to know how many will remain at day 7. So that's going to be my exponent. And when I put that into my calculator, I'm going to get a decimal 0.0078125, which is equivalent to the fraction 1/128th. And the last problem we're going to look at is the growth of elk population.